This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
All right, good morning everyone. So the plan today is to finish off looking at problem set 4, okay, and then we'll start looking at part 4 of the notes, which is about control system design, which we've already been doing through examples, okay, so we're just going to try to formalise some of the ideas in part 4. So last time we were looking at problem set 4. Problem set 4 is about designing a control system for regulating the water level in a stretch of open water channel, which is part of a gravity-powered water distribution network, typically used in a rural setting to get water from some sort of source, like a river or a lake, to end users, that is, farmers. So last time we talked about modelling, okay, for the purposes of control design, and we saw that we can get a good model for how the water level at the downstream end of a so-called pool, a stretch of water between two regulating structures, depends on the flow in to the system and the flow out, which includes a local load and downstream load. All right, and that model looks like this. The reason we can get away with such a simple model is because we're just interested in the behaviour of the water level at the supply points, okay, not the water level all the way along the channel. To describe the water level all the way along the pool, we need a partial differential equation, okay? And the reason we're only interested in the water level at the downstream end of the pool, because that reflects your capacity to supply flow under the power of gravity. It's the amount of potential energy stored in the system at the supply point. Okay, so that's why we're trying to control that. We're trying to control it to some set point level that's determined on the basis of demand. Okay, so we look at the difference between the water level and the reference. That generates an error signal that's processed by a controller that adjusts the upstream flow. And by adjusting the upstream flow rather than adjusting the downstream flow in order to regulate the water level, we end up with changes in the load propagating upstream towards the source, resulting in demand-driven release from the source. Okay, so last time we looked at what can be done with just a proportional gain controller. Okay, we saw that proportional gain control can at least stabilise the system. All right, but there's a limit to how much gain you can have in the controller because of the delay. All right, so the fact that there's delay here, the effect of changing the inflow on the water level downstream is only seen after some time, and because of that delay, there's a limit on how large the gain can be. Okay, so we saw those sorts of things by looking at a Nyquist plot, okay, of the open loop system when the controller was just a gain of 1, okay, and this is the Nyquist plot that you get, right? So it goes around here, whizzes around because of the delay, comes out like this. This is because of the open loop pole at s equals 0. This is what's happening as we go around the little indentation about 0 because of the open loop pole there. Okay, so you can see that if you increase the gain too much, Okay, if we now make the controller some constant k, which is bigger than 1, what's going to happen is that it's going to expand the Nyquist plot. It's not going to rotate it in any way. Okay, so this point in particular will move this way as we increase the gain, and eventually it'll sit on the other side of the critical point, right? Changing from a stabilising situation, as shown here, when the gain is 1, because there are no encirclements of the critical point, which is what we want because there are no open loop poles in the right half plane, to a situation where the critical point would be like sitting inside here, and we would get 1, 2 encirclements of the critical point, okay, which we don't want, right? And we would end up with the critical point in there if we scaled the controller gain by a constant bigger than 1. All right, so there's a limit on how much gain you can put, and there's motivation for increasing the gain, because increasing the gain, as we saw somewhere, is a way of reducing the steady state error for step changes in the load. Okay, we don't get 0 steady state error when using just a proportional gain controller, because we're looking at step disturbances here. All right, but increasing the gain of a constant gain controller will reduce the steady state error for step changes in the load. But there's a limit to how small you can make it, right? Because in order to apply the final value theorem, which leads here, you need to know that the closed loop is stable, right? If you make K too big, it won't be stable. So we also looked at, how you can ensure that, the sensitivity function, the output sensitivity function, 1 on 1 plus lambda, doesn't have peaks than a certain amount, and that corresponded to making sure the Nyquist plot doesn't get closer than some value from the critical point. Okay, so to ensure that the sensitivity function doesn't have a peak bigger than 5, right, we need to make sure that the Nyquist plot doesn't get closer than 1 on 5 to the critical point, right, because the distance from the critical point to a point on the Nyquist plot at any given frequency will be equal to the magnitude of 1 plus lambda at that frequency, right? And we know the magnitude of S at that frequency will just be equal to 1 on that. Okay, so that's why we've had to go to 0.2. It's not 5, it's 1 on 5. Okay. So the last part, okay, so let me just explain some things that people asked about at the end of the lecture. What are all these wiggles about? Okay, even in these transfer functions, those wiggles are there because of the delay. We're dealing with an irrational transfer function here, right? We're not dealing, so if we look at the closed loop, right, the transfer functions look like this, right? They've got this irrational part in them, right? So it's not just, finite number of poles and zeros that we're dealing with when looking at the Bode plots. This term here causes those sorts of wiggles in the plots, particularly at high frequency. Okay, so don't get confused by that. All right. And we saw that, as in the case of a constant gain controller, while increasing the gain of the controller reduces the sensitivity at low frequency, that's what gives us better steady state error for step changes in the load, it leads to peaking in the sensitivity function, which is consistent with one of the frequency domain integral constraints that we saw. Push it down here, it'll pop up somewhere else. Well, here it is happening. Okay, and that's consistent with getting more oscillatory response in the step response in the time domain. So this is not looking at step change in the load, but a step change in the reference. That's why we get 0 error in the end. Okay, you get 0 error for a step change in the reference. Where are we? Because there is an integrator in the plant, right? So that integrator in the plant ensures that the sensitivity function at 0 will be equal to 0, right? And the mapping from here to here is via the sensitivity function, right? Which is 1 on 1 plus lambda s, right? Whereas the transfer function from here to the error is not just the sensitivity function, right? It will be 1 on alpha s times the sensitivity function, all right? So the sensitivity function having this property means that the sensitivity function as a function of s must have a factor s out the front, all right? That's what it means for s to be 0 at 0. It must have a factor like that you can pull out the front. And so when I put that in here, okay, that goes with that, all right? And we don't have the property that when we multiply this by the load signal, right, Laplace transform, which will be 1 on s, we can't cancel the 1 on s on, in the L because of this property, because it's already been cancelled by the fact that we've have to include the plant transfer function when looking at the transfer function from here to here. Okay, so that's why we can get 0 steady state error for step changes in the reference, but not step changes in the load. Okay, the internal model principle tells us that to get step changes, 0 steady state error in response to step changes in the load, we need an integrator in the controller. Okay, so that's what we're going to do in the last part, is we're going to put in an integrator into the controller. Okay, so we're now looking at a controller that has this form, k, it's got a 0, right, and a pole at s equals 0. Right, so that's now putting in the pole at s equals 0 into the controller in a way that's consistent with the internal model principle for input disturbance rejection, right, with 0 error in a steady state. Okay, so you know, what's the impact of that? Well, apart from giving you steady state error, it's going to give you now new constraints on what the gain can be from the perspective of stability and performance, right? The shape of the sensitivity functions over frequency. So given that we have a pole at s equals 0 in the controller, we may not need to have such a high gain k in order to meet our steady state performance objectives, because it's being satisfied by virtue of having a pole at s equals 0 in the controller. All right? So we may not have to push up the gain so much now that we've put that in. Okay, but you know, we still need to check that the closed loop is going to be stable and so forth. All right. So again, we can look at Nyquist plots and Bode plots. All right. The first part is suggesting that a Bode plot be used, all right, to assess the phase margin, right? Which, if the closed loop is stable, will be a positive number, right? For the case where the controller gain k is equal to 0.1. All right. So this is the Bode plot that you get for the open loop transfer function, right, which is the product of the controller and the plant transfer functions for the controller that we just saw, right, with k equal to 0.1. So the controller was this, right? Your plant is still 1 on, right? So what we're looking at for lambda is the product of those two things, okay? So you can see that the phase starts off at low frequencies at minus 180. Why? Because we have two poles at s equals 0, right? And the phase of two poles at s equals 0 will be minus 180, right, for all frequencies, okay? And the phase increases with frequency because of the 0, right? And we've got a pole at s equals 0, at s equals minus 2, all right? And you can see at the frequency 2, right, it's already contributed 45 degrees of phase, right? By the time we get to very high frequencies, it's contributed pi on 2, 90 degrees of phase. Okay, so this going up like this is because of the zero, right? Without that there, it would just be flat at minus 180. All right. Now this is showing what happens when k is equal to 0.1. When k is equal to 0.1, this is the crossover frequency, right? Because it's where the crossover frequency is where the open loop transfer function has gain 1. That's 0 dB. Okay? So the phase margin will be how far above minus pi we are, how far above minus 180 degrees we are. Right? So you can see with a gain of 0.1, we're getting a very small phase margin. Right? And as we've seen, we've got a small phase margin. You'll get peaks in the sensitivity function at around the crossover frequency. Okay, and we've seen the consequence of having peaks in the sensitivity function is when we put step inputs, we get lots of oscillations in the response, right? As you reach steady state. Okay, so something you might consider doing is increasing the gain K to improve the phase margin, right? Because increasing the gain K won't change this, okay? Because the phase of this positive number is 0, so we're just adding 0 to this. Whether the gain's 0.1 or 10 or 100 or 1,000, it's still 0. But what will happen is that this plot will change. If I multiply this by 10, we will move this point up to here, right? So scaling this up will change the crossover frequency. Right? And one of the questions here says, well, what should the gain be to get a phase margin of 45 degrees? So in order to have a phase margin of 45 degrees, we want the phase of lambda to be minus 135 degrees. Right? So that we're 45 away from minus 180. Right? Why is minus 180 important? Well, that's the phase of the critical point. We're trying to make sure that our Nyquist plot's not too close to the critical point. Right? That's what phase margin is about. It's measuring how close we are to the critical point. Intuitively, the closer you are to the critical point, if you're on the critical point, you've got poles, closed loop poles on the imaginary axis. If you're just easing off from there, those poles might be stable, but they'll still be close to the imaginary axis, giving you lots of oscillations in the response. So to figure out what gain gives you a phase margin of 45 degrees, we've got to find the frequency where the phase is minus 135, 45 above minus 180, all right? And we need to choose the gain such that this becomes the crossover frequency, right? So we've got to choose a gain that's consistent with, 30 dB, right? So it's multiplying by more than 10, all right? So, what we're seeing here is a way to use the information in a Bode plot to make a design decision. Okay? And by increasing the phase margin to 45 degrees, by increasing the gain, right, which will just shift everything in the gain plot up by the same amount across all frequencies, well, if we do it right, we can make the crossover frequency there where the phase is minus 135. Okay, and if you look at the time response for different situations, you get this sort of time response, right? So this is when you've got to remember that this is when k is equal to 0.1. So if I'm multiplying by 10, it's like it's not much more than 10 because 10 is 20 dB and this is 30, right? We're making k equal to 1, right? Because 10 times 0.1 is 1, right? So that's what's shown here. When k is equal to 0.1, we're getting this very oscillatory closed-loop response. That's consistent with having very poor phase margin, right? And as you would expect, there would be a peak in the sensitivity function, as we'll see. Whereas when k is equal to 1, which makes the crossover frequency somewhere around here. We get a much better phase margin, and you can see that there's hardly any oscillations, or no oscillations, in fact, in the response. Okay, and that's a consequence of having a better phase margin when k is equal to 1. Okay. In this case, you can in fact choose k to be arbitrarily large, right? And in fact, the larger I make k, the more I push the crossover frequency to the right. By increasing k, what we've done here is change the crossover frequency from here to here. If I keep on going, the crossover frequency will continue moving to the right, and we just get better and better and better in phase margin. Okay, but what we're doing here is not accounting for the delay. All right, we're not accounting for the delay in this open loop transfer function. We're pretending like the delay is not there. All right. If you include the delay, that will stop you pushing the crossover frequency to the right. Okay. In order to satisfy the small gain condition. Right. So if we look at the multiplicative modelling error associated with neglecting the delay in the open loop transfer function, you get the multiplicative modelling error looking like this in magnitude and this in phase. You know, this phase is, you know, it's saying that phase is always modulo, 2 pi, right? So we know that the phase of a delay keeps on becoming more and more negative, right? And I'm just wrapping that around, right? That's really just the phase becoming more and more and more negative. Okay. So in order to satisfy the small gain condition for stability, we know that the product of the complementary sensitivity function, which we're seeing here for different values of k, and the uncertainty has to be less than 1. All right? And you can see that the uncertainty, due to neglecting the delay in the loop in the previous discussion, becomes significant above this frequency. Above this frequency, sometimes the size of the error is bigger than 1. All right? But by restricting the gain of the controller, in other words, putting an upper bound on the crossover frequency, we just saw that increasing the gain of the controller pushes the crossover frequency to the right. Okay, so if we stop at a certain point, our complementary sensitivity function will eventually roll off. And we're making sure that it rolls off in such a way that the product of this and this is always less than 1, so that we satisfy the small gain condition for robust stability. Okay, so this is giving you an example of how you can use the sorts of results that we've seen in design. Okay, now you could have just put the delay in the model, all right? But as we've seen, what that will do, because the delay, the phase of the delay, right, which isn't shown in this plot, but if we put it in, what's the effect of it going to be? It's going to pull it down eventually beyond a certain frequency, right? And eventually it will sit, the phase will be, when you include the delay, it'll be below minus 180. Right? And if you want to maintain a positive phase margin, you would have to limit how far to the right you push the crossover frequency. Okay, but we're seeing the same thing now via, the small gain theorem. Okay, so the point of the examples is just to show you that all of these analysis techniques that we've developed are useful from the perspective of design. We're now using them to make design decisions. In this case, we're using it to put a limit on how big the gain is. Right? What's the advantage of having bigger gain in this controller? We can see that having the bigger gain, shifting the crossover frequency to the right, makes the transient die away faster. Here it takes all this time for the transient to die away. With the small gain, right? With the higher gain, we're getting a faster response. But if you're too fast, because of the delay, you'll get instability. Okay, so you can see how all these trade-offs are arising in design because of different control objectives. Okay, and if you looked at the Nyquist plot, this is what the Nyquist plot looks like when you include the delay. Right, and so the Nyquist decontour that we're doing now has an indentation around the two poles at s equals 0. Right. At very low frequencies, we know we have a phase of minus pi, minus 180 degrees. Okay. As we go up, increasing frequency because of the 0, all right, the phase becomes greater than minus 180, so it's going up, right, and that's consistent with moving down, right, in the complex plane, right. In the complex plane, there's the origin. That's minus pi, right, minus 180. Minus 170 is not quite there. Minus 130 is somewhere around here, right. So this going down like this is consistent with the Bode plot moving up like this, all right. So that's the direction we're moving in as we increase frequency by moving up here, the Nyquist decontour, right. This includes the delay, which is why you get all this stuff whizzing around like this. That's consistent with the phase continuing to become more and more and more negative as we increase frequency. All right. It's causing this point that crosses the real axis in the negative direction. That's like what I just described. If you put the delay in here, eventually this will turn around and cross minus 180 again, right? That's what's happening at this point. Okay, so we're moving around like this. It's whizzing around, comes out, right, as we move back up here. And then we've got to go around the two poles at s equals 0. And what happens as we go around the two poles at s equals 0 here is that we get a net change in phase of minus pi radians for each pole, right? So what's happening here is we're coming out here and it goes around like this all the way back to this guy here, right? Here's 1 pi, one lot of minus pi for one of the poles, and for the other one we get another lot of minus pi, which brings us back to the beginning again. All right? And you can see, well, if we keep on increasing the gain, then this point will eventually move to the other side of the critical point, and we'll get encirclements of the critical point, which we don't want because we have 0 right half plane open loop poles. All right, so there's lots and lots of information in these plots and analysis tools that we've developed. Right, well, lots of information is revealed by them. Okay. Are there any questions on this before we continue? All right, well, the last bit here is about steady state error, and it confirms what the internal model principle says, that if you've got an integrator in the controller, then you can get 0 steady state error for step changes in a plant input disturbance. Okay, but of course to apply that you need the closed loop to be stable. So that's the first thing to check, and we've verified that that's the case for sufficiently small gain K. All right, the controller we've just looked at is just a PI controller. Right, it's a proportional integral controller, as we'll see today. Proportional integral controller gives you a 0, right, and a pole at s equals 0. A left half plane 0 and a pole at s equals 0. All right. So there you go. You've just seen how a real control system in the real world was actually designed. So you guys know already how to design real controllers. Okay. This is pretty much the controller that works in the field, in the irrigation channels in northern Victoria. Okay. Any questions on this? All right. Before we start looking at problem set 4, I just wanted to say something about, where are we here? The example we were looking at 2 lectures ago, which was with the system in workshop 4. Right? So in workshop 4, we're dealing with a plant that has an unstable pole, right? Which is not surprising given that we're looking at a pendulum in the upright position. If you tap it, it's going to fall over. That's consistent with something unstable. I tap it, it doesn't return to its equilibrium value. All right? And we have one stable pole. All right? So with proportional gain, you can stabilise the system, but you'll always end up with a crappy phase margin, right? And so we looked at using a more sophisticated controller. All right. One of those controllers was just a lead compensator, right? And the point of the lead compensator was to try to, so if we look at a situation like this and a controller that just has a constant gain, then we get a root locus plot that looks something like this, right, where they move together and split apart as we increase the gain, all right? And we saw that by putting a 0 and a pole such that the location of the 0 is closer to the imaginary axis than the pole, then we haven't changed the relative degree. So we're still going to get asymptotes that go towards the zeros at infinity as we increase the gain of the controller. So the blue controller here is something that looks like K S plus Z on S plus P, right? Where Z is less than P. All right? So that the pole ends up being further away from the imaginary axis than the 0. Then the effect of that is to move the asymptotes, right, to the left, further away from the imaginary axis. All right? So you end up with, this pole goes to this 0, and these guys, when they come together, they split apart at some point, but then they go towards asymptotes that are further to the left. All right, by virtue of these this pole and 0 here, right? So if you look at where the asymptotes lie, it's the sum of the poles minus the sum of the zeros divided by the relative degree. In this case, the relative degree is 2. All right, and so the effect, so without these guys here, we're getting the anchor point sigma being at this point. All right. And we're putting in this amount into here as a negative number, right? We're putting this amount into here as a negative number. The net effect of putting those two things is to move this point to the left by this amount divided by 2, right? So by moving this pole further this way, we bring them even further to the left. All right, how much we've moved this to the left is this distance divided by 2, right? Because that's how we're changing the top part of this expression for where the anchor point lies. All right, and then we looked at an even more sophisticated controller again. So that's something that's, as we'll see today, maybe not, a lead compensator. All right, and what we ended up looking at was a combination of a lag and a lead compensator, right? So we've got the poles like this, and then we put another pole at s equals 0, right? So that we could get 0 steady state error for step changes in the reference, say, okay, or disturbance at the output. And then we put a 0 in, all right? And then we put, another 0 in and a pole, okay? And, we drew that the root locus plot would look something like this. This guy would go there. And then we had this guy going around, right? Coming around like this. that goes that way, that goes that way, that goes that way. When they meet here, they split apart, and one goes towards that 0. One goes this way, but then it meets this guy, and then they split apart and go to 0's at infinity along 2 asymptotes, right? Because the relative degree hasn't changed from the example above, right? Because for every pole that we've put in a 0. Right, so for this pole we've put in that 0, for this pole we've put in that 0, so we haven't changed the relative degree, so we still end up with just 2 asymptotes. Now it doesn't necessarily do this and come back together again. It could end up doing this, and it really depends on the relative position of these different things, right? Now I can force it to do this by moving this really far to the left. All right? If you didn't put that extra pole in, we would be in a situation like this. So here's my unstable open loop pole. Here's my stable open loop pole. I've put this guy in. Let's put this guy in and just have a 0 here. Okay. So now I've made the relative degree, I've changed it. I've made it equal to 1, right? Because I haven't put a pole to associate with this guy here. Right, so I've got 1, 2, 3 open loop poles and 2 open loop zeros, so the relative degree is equal to 1. So this only has 1 asymptote that goes towards the 0 at minus infinity. All right, so this guy does always behave like this. Yeah, I can't draw circles perfectly, like this. Okay, that one always does like this. And it really doesn't matter where the anchor point is, right? When you've only got the asymptote going to minus infinity, right, it doesn't matter where the anchor point is, right? Because I can have the anchor point here, the asymptote still goes to minus infinity. I can have it here, it still goes to minus infinity. It doesn't matter where the anchor point is. The anchor point, there's no information in the anchor point when the relative degree is only 1. Okay? So, the fact that if I put a very high frequency very fast pole down here, then it's going to look something like this. And why might I put a really fast pole in here? Well, to make sure that my controller is proper, right? If I don't put this guy in, then my controller is not proper. It's got 2 zeros and 1 pole, right? And we've seen that you can make controllers proper without affecting what's going on much by just adding a very fast pole. And so if I'm adding a very fast pole, it's probably still going to do this, and then this and this guy is going to meet together and go off like this, right, as I showed originally. But, it really depends on how fast you make this guy. All right? So it could end up looking like this instead. It could end up looking like this. These come together, they split apart, right? This guy is to here, this guy could go to here, and these guys could end up going up the asymptotes. But what's the difference? There isn't really any difference. For high gain, what we get in this situation is always 4 closed loop poles, right? We're getting 1 here, 1 here, 1 here, and 1 here. Right? For small gain, we're getting 1 here, 1 here, 1 here, and 1 here. But for high gain, we're getting 1 here, 1 here, 1 here, and 1 here. That's exactly what we get here. For high gain, right, we end up with 1 here, 1 here, 1 here, and 1 here. Right? So the exact shape wasn't important within the context of what we were discussing. We were just trying to figure out, well, how can I locate these roughly relative to each other to get some desired result? Okay, so don't get hung up always on the details of, but I went away in MATLAB and I typed this in, I didn't get this, I got this. Or if you interpret it in the right way, they are the same thing. For high gain, we get the same outcome. And to get the outcome that we want, we have to have high gain, because the outcome was about trying to make sure we had very good damping. And with the closed loop poles here and here, we're getting good damping because the real part in magnitude is much larger than the imaginary part, and that's what good damping corresponds to. Okay? So make sure that you're thinking bigger picture when looking at unexpected outcomes, right? Try to interpret what these things mean rather than, oh, this has got different shapes, so it must be very different. But if you stop and try to interpret, you see that they're actually the same in terms of the result that we were trying to achieve. Make sense? Any more questions on that? All right, let's just start looking at part 4 at least. I've had several false starts already, so let's at least start it so that next time we'll definitely be there. What are we doing? Part 4. Okay. So this is just stuff. It's a little preamble. We know this stuff. We've been discussing it lots of times. And we've seen it within the context of examples now. So, control system design, I think a useful way to think about it is in terms of how the open loop transfer function is shaped across frequency. And we've seen that, it's in terms of meeting steady state performance requirements, it's good to have high gain at low frequency where, references typically have most of their energy and disturbances have most of their energy. From the perspective of robustness and reduced sensitivity to sensor noise, we've seen lots of times already that it's good to have an open loop gain that's small at frequencies that are high. All right? And so it's knowledge of the type of reference and disturbances, the model error, sensor noise, where the plant gain is small, because we don't want to have high controller gain where the plant gain is already small, because that can lead to actuator problems. All right? Gives you these lower and upper bounds on the crossover frequency. Right? Information about these things tells you where this has to be high and where this has to be low. Right? That gives you the lower and upper bounds on the crossover frequency, because it's only high below the crossover frequency and only low beyond the crossover frequency. All right? The real challenge is about making the transition between high gain and low gain in the right sort of way. As we've seen, the phase is very important at the crossover frequency, right? How close the phase is to minus 180 determines how much peaking we get in the sensitivity function. And we've related that to how much oscillation there is, how well damped the closed loop response is. Okay, so clearly the closer these are together, the steeper the transition will have to be. And as we'll see later on, the steeper the transition, the worse the phase margin. All right? So control design becomes very, very difficult when these are close together. But what does these being close together mean? It means that we can't really separate out our competing objectives, the ones that are telling us to make it high gain and the ones that are telling it to make it low gain. All right? And in situations like that, well, you've got to do something. You've got to change some part of the setup. You've got to buy a different sensor or build a better model or ask for less performance from the perspective of reference tracking and disturbance rejection. Right? Or don't use feedback. But then if you don't use feedback, you really need a very good model. All right? Really a lot of control design is about worrying about this part of the open loop transfer function. It's easy to pump up the gain, and it's easy to roll off. To roll off, we just need to put poles in, that roll off, right? How can I get high gain at low frequency? Or I just put an integrator into the loop. That'll give me infinite gain at zero frequency, right? So achieving high gain here and low gain here is easy. The hard part is making the transition sufficiently smooth, all right? So we often think about control design in terms of compensating the open loop plant transfer function. So we've been calling that G. What we're looking at here is lambda, and lambda is the product of the controller transfer function and the plant transfer function. So we often call this a compensator. It's compensating the shape of the given G to give us a desired open loop shape, something that looks like this in a fashion that's consistent with our performance requirements and the limitations of our sensors and the model we have. All right? So that's why we often call this a compensator. All right? Now, how do we, we don't, always have lots of information about these sorts of things, okay? But you can often think of how the closed loop is going to behave in terms of dominant second order dynamics, all right? And, the reason for thinking like this is that if I have an open loop gain that looks like this, it's high at low frequencies, then it makes a transition at the crossover frequency and is low at high frequencies, then the complementary sensitivity function, so this is lambda, right, and it's the magnitude of, the complementary sensitivity function, as we've seen many times, because lambda is large at low frequencies, it will be close to 1, so this is 0 dB, right? And then it'll be 1 over a range of low frequencies. It'll look like this at high frequencies. It'll roll off like lambda, right? So this is T. It's lambda on 1 plus lambda. And in the middle, well, it could peak up before rolling off. It really depends on the phase margin, right? The smaller the phase margin, the bigger the peak there. But if you look at this, what does it look like? It looks like the Bode plot, or at least the magnitude plot, of canonical second order dynamics. Okay, if I plot the Bode plot of that, it looks like this. And how much peaking I get depends on the amount of damping, right? If the damping factor is bigger than 1, it does this, right? If the damping factor is a small number, it does this. Okay? And, where we are sitting here is related to the natural frequency. Okay, so for bigger natural frequency, this will be further to the right. For smaller damping, you get a bigger peak. So we can often approximate the closed loop complementary sensitivity function in terms of canonical second order dynamics. And this allows us to translate time domain specifications into frequency domain specifications, right? What are we looking at here? We're looking at this being the crossover frequency, right? That's going to be related to, the coefficients here in the transfer function for a canonical second order system. The phase margin is going to be about how much peaking we have here, all right? So we know the time domain behaviour of a canonical second order system, and so we can use that to help us translate time domain specifications into frequency domain specifications. So we know, for example, that you get this much overshoot, right, for canonical, in the step response for a canonical second order system, right? We know that the settling time is related to the product of the damping and the natural frequency, right? The settling time, is about, 4 or 5 time constants. The time constant here is the product of the damping and the natural frequency. You saw all this stuff in workshop 1, right? So, you could ask the question, well, what does the open loop transfer function have to look like in order to get a complementary sensitivity function that is exactly this, right? Well, if I know what I want the complementary sensitivity function to be, this tells you what lambda needs to be, and it's really just about rearranging this equation, right? So that we now express lambda in terms of t instead of t in terms of lambda, right? So it's saying that you will get exactly canonical second order dynamics, with desired overshoot, which relates to the damping, and desired settling time, right, which relates to the product of the damping and the natural frequency, by having an open loop transfer function that looks like this. Right, it's got a 0 at s equals 0, and it's got another pole. All right, and so we can now translate these specifications, settling time and overshoot, which gives us specifications on the damping and the natural frequency, into what the crossover frequency should be, via this being the corresponding open loop transfer function, and a corresponding phase margin which depends on the damping. Okay, so this is often a tool that's used to translate these time domain specifications into frequency domain specifications. All right, and it works well as an approximation as long as your open loop transfer function looks roughly like this at the crossover frequency. All right. So these are just some plots that show you what these functions look like, right? So that you can use them to say, well, if I want a certain amount of overshoot, right? If I want there to be 20% overshoot, then I need a damping ratio of this, and if I want a damping ratio of this, I need this much phase margin. Okay, and then this is telling you how to figure out the crossover frequency in terms of how it relates to the natural frequency of this canonical second order dynamic. So it's really this equation here, right? So it gives you this tool for translating time domain specifications into frequency domain specifications, and it works well as long as I said, your open loop transfer function looks roughly like this ideal open loop transfer function, which gives you exactly canonical second order dynamics, right? So this little example here is just about showing you that, well, it doesn't really matter. As long as we have high gain at low frequency and low gain at high frequency, right? As long as we approximately look like this ideal loop shape around crossover, we get pretty good match between what's predicted by this approximation and what's actually achieved in terms of closed loop settling time and damping, overshoot and so forth. Right, so they're the simple points that I just wanted to make today to make this link about, how do we convert time domain specifications into desired loop shape. Well, if we want canonical second order dynamics with specified damping, right, which affects the overshoot, and specified settling time, how fast it has to be, then we need to make our open loop look like this. Okay, especially around crossover frequency, as long as we have enough gain at low frequency and sufficiently low gain at high frequency. So what we'll start looking at next time is how to achieve that desired loop shape by using combinations of simply parameterized compensator forms. And through the examples that we've looked at, we've already seen them. These things, lead compensators, PI compensators, and so forth, right? So we often use more than one at a time. You don't just use one, all right? And we'll have a look at that next time.
So actually, want to push the asymptotic lines like much back. I think that because it allows we have a K bigger and at that case the response time will be faster and smaller.
We can't tell because the very locus plot, the very locus plot is giving you different values of K. So the different points you have are different values of K.
So for large K,
large K, you end up well down the path, right? Yeah.
So how do we consider from this line to consider the sensitivity of the we can have large gain to make the real parts much bigger than the imaginary part?
Yeah, that's what you want. For having small peaks in the sensitivity, you want the real part